Hi, this is a walkthrough for the Advanced Mathematics Trig Identities and Formulas classwork, Part B, pages 1 and 2. If you are having trouble working through this section on your own, feel free to take a look at this video to get a tip or two, but try to do it on your own first. As you look at this page, you should be reminded of an application question that we did some time ago for right triangle trigonometry. And in that application, we were given this basic diagram with the 45 and the 30-degree angle, and I think these two segments being congruent, what you had to do is figure out a length for this, and you could use a symbol or you could use a number, and then also figure out all these other angles first, and then using right triangle trigonometry you could work out all of these side lengths in terms of this original value here. And what we ended up with was coming up with this side length, this little segment here, and this entire side length here. And then that meant, because we knew this hypotenuse for this right triangle, that we could figure out what the sine of 75 degrees was, and the cosine of 75 degrees, and the tangent of 75 degrees. And when we did that, it didn't end up mattering what our original value was that we chose here. We always got the sine of 75 was something like this, or equivalent to that, cosine and tangent of 75 degrees. Pretty cool. 75 degrees, now that we've done unit circle work, you remember that 75 degrees is not one of our magic angles on the unit circle, but it does have an exact value for sine, cosine, and 75 degree tangent of 75 degrees that's easy to represent. So it's an irrational number, but you can express it quite easily in terms of root 6 and root 2, and for the tangent, root 3. So we're going to take that idea and expand on that a little bit. So this was a case where we're getting the sine, cosine, and tangent of 75, but it turns out that 75 degrees is the sum of two angles that are in the unit circle. So we want to generalize this result. So on to page 2. Now we have the same diagram, but we don't have any of the angles actually identified numerically. And we want to do sort of the same thing we did for that application. We want to find out all the side lengths in terms of sine A and cosine A and sine B and cosine B. So let's see where that leads us. So we've got in this upper triangle here an angle A. It's a right triangle, which means that this over here is going to be the complement of A, 90 degrees minus A. And that means that this angle, if this angle plus this angle plus this angle have to add up to 180, and this angle is 90, then it stands to reason that this angle is also going to be the angle A. And then that means that this angle down here is going to be the complement of A. And let's see, what else can we figure out here? Oh yes, this is going to be the complement of B. And since all three of these angles have to add up to 180, if we added what we have right now, we'd have 180 minus A minus B. That means that this angle here has got to be A plus B. And that's the same result we saw on the application problem. We had 30 and 45 degrees for the A and B, and we ended up with this angle down here being 75. So let's look at this triangle here, we have a right triangle. Its hypotenuse is 1. So if we start looking at angle B itself and we try to sort out what the size of this side is going to be, that's the adjacent side for angle B. Again, the hypotenuse is 1, so if the hypotenuse is 1 and we're looking at the adjacent side for angle B, that means that this is going to be cosine of B. Try to write that a little more clearly. Now, this other leg in that triangle, if that one's cosine, then the other one's going to be sine of B. It's the opposite side. Again, because the hypotenuse is 1, it's just sine of B. Right, now let's look at the top triangle, the one with angle A in it. If this hypotenuse here, and again, this is the hypotenuse for this right triangle up here. So this wasn't the hypotenuse for this triangle, but for this triangle on top, this is the hypotenuse. If this were 1, then this leg would be the adjacent side. It would be simply cosine of A. If this were 2, then this triangle would be twice as large as that, and this wouldn't be cosine of A. It would be 2 cosine of A. It would be twice as large. If this were 10, this would be 10 cosine of A. See the pattern? Well, this hypotenuse is cosine of B. That means that this is cosine of B times larger or smaller than cosine of A. Well, let's write this then and see, make it clear. Okay, so this is going to be cosine of B times cosine of A, because this hypotenuse is not 1, it's cosine of B. So this side length here is scaled up by whatever the length of the hypotenuse for this triangle is. We can tell that this is true by saying, cosine of A is messy handwriting. Cosine of A is adjacent over hypotenuse. And using the values that I've got here, I have cosine of B, cosine of A, hypotenuse is cosine of B, cancels, equals cosine of A. So this works. Cosine of A is cosine of A. In other words, the ratio of that adjacent to the hypotenuse is the cosine of A. That's all we're getting at. Likewise, the opposite side in that triangle is going to be cosine of B times sine of A. All right. Now, if we go down to this little guy down here, similar things going on. We're going to work with angle A. We have a hypotenuse that's equal to sine of B. So the adjacent side to angle A is going to be cosine of A times sine of B. Again, it's not just cosine of A, it's cosine of A times sine of B because the length of the hypotenuse is sine of B. If it were 1, then this side would be cosine of A. But because it's not 1, it's cosine of A times the length of that hypotenuse, which is sine of B. So altogether, the length of this side is cosine A sine B. All right, now I'm going to write this other leg down here. So opposite for A, sine of A scaled by sine of B. So again, if that hypotenuse had been 1, that leg would just be sine of A. But because the hypotenuse is not 1, sine of B, it's sine of A times sine of B. So I'm going to write the next line just a scooch lower. So we want to figure out sine of A plus B. So here we have angle A plus B. This hypotenuse for this right triangle over here is 1. That means that this opposite side is just going to be sine of a plus b. I can go and write that in. That is sine of a plus b. And this is all in parentheses like that. So we take the angle A and we add it to B, and then we take the sine of that. And that's what the length of that side is going to be, because its hypotenuse is 1. Now, remembering what we did in the application problem, you remember that this entire side length is equal to this segment plus this segment. So that means I can write down here sine of a plus b equals sine of a cosine b plus cosine a sine of b. All right. So sine of the sum of two angles, sine of the sum of a plus b, is identical to taking the sine of the first times the cosine of the second, and then adding to that the cosine of the first times the sine of the second. Okay. Now, the cosine one, that's this side over here. That's adjacent to a plus b, so that's cosine of a plus b. And that's equal to this whole side length minus this one here. Now I'm going to write this, and you'll notice I did this one here, sine a cosine b. That's this one. I reversed the order of those two functions because it doesn't matter what order you multiply numbers in. And the reason I did that is so that I have a consistent ordering of the arguments. So this is sine of a times cosine of b plus cosine of a times sine of b. And I want to keep that pattern going down here, and you'll see why in a little bit. So first thing is going to be cosine of a cosine of b and minus sine of a sine of b. So we've got now these two rules, one for when you have the sine of the sum of two angles, and another for when you have the cosine of the sum of two angles. And these are different rules. This is sine, sine, cosine, cosine, sine. This one's cosine, cosine. Sine is different. Sine, sine. Sine, cosine, cosine, sine. Cosine, cosine, sine, sine, sine. If you want to kind of remember that. But they're very different, but they sort of accomplish the same goal of an equivalent statement to the cosine of the sum and an equivalent statement to the sine of the sum. And I think, yeah, that wraps up page 2. So if you find the video for page 3, we'll go a little bit further with this. If that's all you needed help with for now, go back to the classwork and see what you can sort out on your own.